Complexity speaker series talks. We're starting off with a bang with Professor David Krakauer, who's the president of the Santa Fe Institute. I maybe don't need to give a super long introduction because my hunch is that everyone knows who he is. Everyone is eagerly awaiting his perspective today. So with that, please take it away.
Thank you, Brandon. Wonderful to be with you. This has been great. This is like jumping from one Santa Fe Institute into another. It's like a lot of friends here. The way I would like to do this is more like a seminar than a talk. So please just interrupt me as I move along because it's kind of new ideas and I would love to be able to steal your better ideas. And so if you have observations to make, I'd be delighted to hear them. So don't hold back on and certainly for clarification. So this, yes, so this comes from, how many people have gone and have seen this painting or remember this painting, which is just down the road in your museum here, by the way? Not many, wait, zero, okay. So you should go to your museum, because it's beautiful, and in it there's a room of surrealist paintings. And this is Agnes Pelton. It happens to be an artist I really like. She's called a desert transcendentalist. She was German. She was born in Stuttgart. She moved to New York and then was a student of Arthur Dow's. So if you know your art history, Arthur Dow was also Georgia O'Keeffe's instructor. And through that connection, she went to New Mexico. And in 1918, and then fell in love with the desert, as I have. And unlike me, she paints beautiful things that she sees. But this painting that has this kind of physical world of mechanism, a sort of a funny little living world, perhaps in the intermediate, and then this world, the abiotic world of crystal forms, kind of I want to touch on these ideas. So this is basically what I'm interested in here in one slide. Is that clear without reflections? I wonder if, because it might be a little easier if that's a bit, right, yeah. And I like my color palette. Yes. Yeah. And so, yeah, because they're often so bought, use color. Color is your friend. So the first question, right, is, could you conceive of a form of life that was not intelligent? Does life always imply intelligence? Okay, that's the first thing. And I have to say, I think so. Some people think life and intelligence are the same thing, and I'll try and convince you that isn't the case. But I think you could make the claim. And the second point is the reverse true? Right? Does intelligence imply life? And that I think is harder to argue. You know, you might say an LLM, I don't believe this, but you might say an LLM is intelligent. Is it a form of life? I don't know. And I would like to be able to answer these in a very principled way. So that's sort of the big thing. So now that I'm going to give you my worldview, so-called Weltanschauung. The Germans have the best words for these things. And so, okay, so here's a paper that your neighbor here, Mike Levin and others wrote. And Mike wrote to us, a number of people, and asked us for our definition of life. So what is it? Tell us. And honestly, these definitions are horrible. And so there's Ricard, one of my colleagues at SFI, also based in Barcelona. Life is a dynamic, self-sustaining collective property emerging by exploiting self-organization of soft matter and so on. There's nothing wrong with that per se. It's just that it's a bit of a list. And the next one is better. Life is the pattern and process of, who mentioned this to me yesterday? Life is the pattern and process of love. A deeply vulnerable, mutual dance. I thought, my God, you know, I wish that were true, you know, but I'm not sure. An E. coli, I don't know, would look at that and say, that looks familiar. Anyway, on it goes. My definition was so short, they didn't even include it in the paper, much to my annoyance. But they did include me in a plot. Then they did some kind of multidimensional scaling thing. They turned those sentences with long word frequencies into some kind of, in fact, in this case, it's some kind of conditional probability KL divergence game. And here I am with my colleague Walter, who's here, a neighbor in Harvard, Walter Fontana. And basically, there are some of us who are interested in definitions of life that look somewhat cognitive, kind of computational, I guess. And there are others up here in sort of pink who tend to emphasize biochemistry. And in fact, most of the history of studying the origin of life has been looking at prebiotic chemistry. That's changed somewhat. And so I'm a functionalist. I don't think it really matters what you build it out of, although it matters that it's matter. But I'm not sure the matter matters. So that's a bit on life. And the point is, of course, that this field has been around quite a long time. There's no consensus. It doesn't mean it's not scientific. It's okay for complex concepts to support a plurality of different perspectives. I get very frustrated when people tell me, what's complexity? No one agrees. Thank God. I mean, that's like love. It's like life. Good concepts support a plurality of perspectives. Weak concepts have single definitions. Okay, so here's my definition that they excluded. Autonomous problem-solving matter. Something spoke just now. Okay, and I'll try and explain autonomous problem-solving matter to you. This has been a long-term interest, and I just ask you, do you think the left or the right is autonomous problem-solving matter?
B.
Any A's? No A's, why not? Yeah, I'm with you. I think B is more compelling than A, and it's interesting to ask why. Oh, here's a little video of one form of matter in competition with another. It's actually an amazing video. I should show the whole thing. It's so cool. Yeah, that's Buster Keaton at his best. And you could you looked at that and I said, which of those things is not like the others? I think you'd probably pick Buster Keaton as being a little different. He might have been hurt in the making of this. Okay, because there are people out there who say things like, what's the difference between life and a ball rolling down a hill? And I'll tell you, and so that's basically the physical world, right, is governed by the principle of least action. Right? You solve the action functional for the stationary action. That's what everything does. That's what light does moving through a vacuum. That's what particles do in fields. This is the world of physics. Adaptation adds something to the action function. It actually endogenizes memory, right? If I have a ball, the ball doesn't know where to be put on the hill. It'll roll down the hill, but with adaptation, you know where to go on the hill, and then you can roll down the hill. So in that sense, there's an element of adaptation that looks a bit like physics, but you're adding state information above and beyond the action function. And then the agentic world that we're all so interested in now adds something else. It adds the future. Adaptation adds the past, and agents add the future through a policy. So now you have a statement of not only does the local curvature of my fitness function tell me where to go, not only do I know where to be in the landscape through a history, but I'm actually going to make decisions which are not dictated by the current state of the world. Right? So that's the spectrum from, I think is that me? I hear a kind of echo. Okay. From the physical universe all the way through to the agentic universe. And a few years ago, we wrote a paper where we tried to formalize these ideas. So for those interested in this, here it is, where we actually do a decomposition into the bit that you'd call, in some sense, policy-like, the bit that's environmentally determined, more like physics, and the adaptation part, which is about memory of the world. Okay? So that's life. Yeah, of course.
There's also notion of policy that you're trying to learn policy.
Yeah.
When you say policy here, Is it similar to
Yeah.
what, like, reinforcement learning people would say, I'm trying
Yeah.
to learn policy?
Yeah, it would be similar. But, right, because a policy, so reinforcement learning here might be natural selection, right? And you're trying to consolidate a series of decisions that would work under a range of environments, such that if I looked at the instantaneous state of the system, if I didn't have access to its internal state, the internal policy, I couldn't predict its future. In fact, life is like a violation of the action principle. If a ball rolls up a hill, you might say, ooh, it's agentic.
Right.
Right, and that's encoded, for example, in a policy. So what about life or intelligence? We've done the definitions of life, which were weird. What about definitions of intelligence? This is even bigger, and I actually have a paper where I'm actually going through all of these definitions at the moment. And it's kind of endless. I've just put up a few. This is a very famous quote from George Romanes. George Romanes was Darwin's assistant at the end of his life. Reason or intelligence is the faculty which is concerned in the intentional adaptation of means to ends. It's not just, so that's like policy-like. It's not just adaptation, right? And on they go. But what's interesting about this list of definitions is I can do a substitution and just put life in there. And if I said, life is the faculty concerned with intentional adaptation of means to ends, life leads to successful adaptation of a wide range of environments. Life is the capacity to acquire capacity. You'd say, yeah, that's right. So there's something weird going on here, right? That we can kind of effortlessly move between intelligence-like definitions and life-like definitions, and you don't lose much. Yeah.
I think for number 3 here, it's definitely not correct.
Yeah, life, it's the hardest one. Yeah. It might. That's Skinner's. It's the weirdest, admittedly. It's the tightest fit to the shoe. Yeah.
So, if you argue that successful adaptation, going back to this previous slide, requires some kind of agency?
I mean, they're on a agentic spectrum. And I think that to that extent, yes, but minimally, right? Because you could, the clearest example is something like bacterial chemotaxis. So there you're basically processing a bit of information. And essentially the behavior is almost perfectly predicted, subject to errors, by the gradient. So there's nothing surprising, really. You could infer it. And as a more that's actually really interesting, as a more intelligent person. So there's almost a perfect correlation between a kind of a scalar field and the behavior of the system itself. And so I actually view intelligence as violations of expectations given knowledge of context. So we've done this game where intelligence looks a bit like life. Now I want to ask the following question of this room. What's more alive, a dolphin or a bee? Yes, please.
So the dolphin, as given your definition, would it be like more autonomous in the sense that maybe a bee is not the best example, but if I think of like a bacteria that violates that action principle, I feel like they're violate less than the larger ones.
Yeah. Okay, good. Okay. Anyone disagree with that? Yes. Sorry? The base meaning? Oh, I see. More alive. Okay, that's a good. But is it even meaningful, even without a baseline, to establish the hierarchy where you say there's more life in a species than another species? You think you can do? Okay, that's.
Because I think it's a very human-centered question.
Okay.
But generally, if I'm a bee, I can say I'm more.
Yeah, I would.
Just a thought. Is what we do.
Okay, well, okay. All right, let's get there. That's interesting. Did you ever?
Mammals are more alive.
Mammals are more alive. My God. Okay. You guys are so anthropocentric. Yeah. Yes.
I mean, are we thinking of life as some kind of like
quantity descriptor, or is it, oh, if you have more mass?
Okay, so I'm going to get, okay, I'm going to get there. So who's more intelligent then? I mean, anyone got any bee person here?
One, maybe not.
Oh, right, but even a hive, I would argue. Yes, a powder. Okay, but the interesting point, right, is that this would generate some controversy and argument about whether one can even have an inequality. Whereas here you'd say, maybe it's the bees, but you would accept the fact that it's not silly to say that something can be more intelligent. It might be silly to say something is more alive.
Yeah.
So, okay, so I'll tell you why. And I'm going to argue, right, that life is intensive. So this is from statistical mechanics, thermodynamics. And intelligence is extensive. And let me just make that clear for those who don't know this terminology. There are lots of variables of state in thermodynamics: temperature, entropy, pressure, volume, voltage, charge. And these on the left are all intensive. They don't scale with system size. So you can have a room that's 4 times bigger and it's the same temperature as a room that's a quarter the size. Right? But you have to, by definition, if you have more particles in a larger room, have a possibility for higher entropy by Boltzmann's equation. There are more possible microconfigurations. So these things over here have the character typically of forces or potentials. And these things over here have the character of quantities or displacements. And I'm going to argue that actually intelligence is like the conjugate dual variable of life. If life is something like a potential, a selection gradient, it's the accumulation of states that defines intelligence. And that's why it doesn't make sense to say something is more living than something else, but it makes a lot of sense to say something is more intelligent than something else. Okay?
So what would we get rid of this Heisenberg's principle as a conjugate pair?
No, I mean, actually, it's interesting. So I'm now trying to see how far I can push this. Like, can I write down the Legendre transfer on a selection function to derive something like the number of bits stored? Right. But people get the idea, right? And I think it's clearly sort of right. The question is, how far can we push it formally? And just to show you, I mean, you can write down generalized selection equations for any system. It could be an elephant, it could be a micro, it doesn't matter. You guys are always writing down network equations, and they're kind of scale invariant, right? But over here, they shouldn't be, right? Because here, right, we should be saying something about, there's something about the system size that matters. And what I'm going to tell you is I think it has to do with 3 dimensions of experience. One is a dimension of space, one of time, and one of sensation. Yes?
In regards to that definition of life before, you like talk about intelligence as units of like
You probably could. Yeah. I mean, the question is, right, whether you want to be, you could, I mean, and I've done this actually, you could say, oh, I want autonomy to be on a spectrum, right? So there's more autonomous or less autonomous. And to the extent that you equate that with the agentic, yeah. It's an interesting question of, because I want to say something like a virus is very agentic, right? But it's probably not inferentially, representationally very clever. So there's a certain dimension in which it is and other dimensions in which it is not.
And it has to do with the like 3-dimensional ness of intelligence.
Exactly. Yes, exactly. Thank you. Yes. For those who don't know, this A student over here, or A faculty or whatever you are, I have been interested in these different axes, you know, representational capacity, inferential, and strategic. And I think, yes, I think a virus, strategically, a kind of genius, but not, you know, not painting Agnes Pelton paintings, right? Okay. So where is, why? Yes, sorry, go ahead, please. That's where I'm going. This was just all foreplay. And the reason it's important to me is because I'm trying to get you to accept this idea of intelligence as extensive. And then the question is, what happens when you hit the boundaries of extensivity of the organism? And so now let me get into that artifact. So this is one of those beautiful images of a zebra fish brain, you know, doing its thing. And so I'm going to kind of make this argument now for the rest of this talk, which is the substance of the talk, that intelligence is emergent from life. So then you have to say, what, oh no, you've now introduced a third concept that no one knows what it means, emergence, right? So, okay, so let me do that. So there's a famous paper that Phil Anderson wrote, we talked about it yesterday, in 1972, called More is Different. In some sense, it's like the manifesto of complexity science. And Phil won the Nobel Prize in condensed matter. He's working at Bell Labs and worked at Princeton. And what Phil said, right, is that, so what's more, he was actually thinking about the scale of a system, just how physically large it was. And different was, just for those who are not familiar, is as systems get larger, symmetries get broken, and the underlying laws, which might be, say, time symmetric of physics, don't really help you explain what you see, because what you see is an accident of history. So at a certain point, the physical laws lose their predictive value because they don't pick out the observed states. History picks out the observed state. That's what he meant. And so what's more here? More is more autonomous problem-solving matter. That's what I mean by more. There's no difference between you and a chimpanzee, just got more of something. And the question is, what's the difference? And the claim is here, and this will be the rest of the talk, is that what intelligence is really about is you use more of something to make difficult problems easier. So here's my definition of intelligence: making hard problems easy. Okay? That's true for a bacterium, and it's true for a mathematician. It's true for a dancer, and it's true for a piano player. Right? Stupidity is making easy problems hard. Okay? It's very interesting why stupidity persists, particularly now in the world. and we can talk about that. I think it's a very important problem. But I just want everyone to see that my definition of intelligence is as short as my definition of life. So I'm consistent. So basically, in a lot of former work, I've been trying to show how more makes something different. So here was all these embarrassing papers that we wrote on the statistical physics and biophysics of molecules, all to show that if you have more molecules, you can have digital switches instead of analog ones. Who cares? I talked about this yesterday in our reading group thing, and this is work on, you have more neurons, you can encode receptive fields that you couldn't do with 1 or 2 neurons. So it's really different, and different means, right, that if you have enough of these things, you can project onto a low-dimensional manifold. And that thing has a shorter description length of all of the inputs to it. So you're familiar with this in neural nets, right? We're always looking for these low-dimensional encodings. So that's what, in this case, different would be. But you need a lot of things, which is the paradox, to find the simple thing, okay? So now we get to cognitive artifacts. Thank you. Yes, of course.
So with the coordination, is coordination stochastic, or is it deterministic? So in the previous slide, you had independent and you had coordinated. I'm interested in what you mean by the coordination. Is it stochastic? How do you see it?
So this is a paper on where the receptive field is a flow field. It's motion, the perception of motion. And what you can show is, if you look at cells in a certain part of the brain, there's a phase in which they're independently sampling the input. And that's great because you get this IID type thing. And then at a certain point, they're bound together very tightly and they become coordinated. And they all then have the same opinion. So this is now, there is stochasticity in this, but they're actually accumulating knowledge of the world.
But the stochasticity is in the independent, in the IID stuff, not in
Yes.
coordination.
No.
So the coordination is dense, we all like...
Correct. Correct. Correct.
That's not interesting.
It's interesting in the following sense. Here's the sense in which it's interesting, which is here, look at this lecture. Everyone has independent opinions, right? You haven't yet talked to each other and you said, oh, what is David talking about? I don't understand. Nonsense. Afterwards, you might conspire and then form a clique and come to a consensus. And most of our activities have this dual kind of structure where there's an independent phase, like this, and then a coordinating phase. Like it gets into a textbook or something. And they're both important. And actually in the brain, I can tell you, not what I want you to talk about, but I'll tell you why it's important in the brain. Because let's say in this population of cells, one cell has the answer. How do I know I'm another part of the brain? I need to ask a cell, what's the answer? And if I ask a random cell, I might get the wrong answer. And what the coordination phase is, it creates sufficient redundancy such that the downstream brain can interrogate any cell.
But there's a price to anarchy here, right? Like if everybody's connected to everybody, then I have to ask everybody, right? So that's some deficiency going on.
There is. Let's talk about it. There is. Yeah, no, but it's a good point. Yeah, no. And it's a kind of an enforced biamplitude in the case of the brain. But it's this really interesting point. I've often wondered, how does, when you're trying to solve the binding problem, like this is an orange, it's a sphere, and it smells like this and tastes like this. How is that all communicated in a consolidated fashion? How do I know which cell to probe? And the way the brain solves it is it goes through a phase where all the cells agree.
Because like as computer scientists, we love randomness, right? Like the random algorithms, and they solve things extremely well. So there is some coordination going on, but there's a lot of randomness.
Yeah, and that's true here, and that is definitely true. You want both phases.
That's a clarification.
Yeah.
You say difficult problems, you mean longer informational description length?
Let's go. You keep preempting me. You just have to be patient and enjoy the narrative. And so, okay, so let's jump into that. I'll show you what I mean by it. Yeah. So one of the characters, no, it's good. It's what I asked for. It's just that he happens to ask the question just before this. And so, if you look at humans, it's kind of interesting fact, right? It's not just that we solve math problems and have high IQs and all that. It's that we surround ourselves with material objects that have an inferential character. They kind of do what the brain does. And writing systems, artworks, maps, sextants, quadrants, all sorts of navigation instruments. And as you can see where I'm going to go is that to the extent that intelligence is extensive, we can extend both into collectives, yes, or you can extend into matter. And what I've been interested in now, and I think Gucci might be online as well, various collaborations, is how does extending thought or mind into matter improve intelligence? What's this one? Oh yeah, and there's lots of work on this. It's really interesting. This is a famous book by de Groot on chess. So it's very hard to know how to answer this question, right? It's like, what am I going to do? Study calculators? You have to pick a model system, and we were talking about that this morning, that's sufficiently tractable and sufficiently rich to be illuminating. And I actually think one of my gauges of the quality of a scientist actually is how well do you pick your model system? Like Schrodinger, Heisenberg, Dirac, pick the hydrogen atom, right? It's like the simplest thing that still had everything they wanted, right? And that's kind of what the game you want to play. If you're studying intelligence and you say, I'm going to work on how Newton developed his theory of optics, I'd say to you, probably not going to do very well. Okay. And so chess is one of those things that has that character, and you can study it, and there's a database and archive. And there were some interesting observations that have been made, this point about what experts do that rhymes with my remark about making difficult problems easy, right? This is famous work by Chase and Simon, where they look at perception. That's where they introduce the idea of chunking, that people see configurations, common patterns on the board that they commit to memory. And this kind of that statement. And then this point, which I think is really important, that perception and memory are more important differentiators of chess expertise than the ability to look ahead in selecting a chess move. When I grew up playing these games, I thought being good at chess was like enumerating the game tree. That's what crap people do. What good people do is not that. And here's a nice study. Oh, damn. I want to show you this study before. Wait. Oh, go away. I'll come back to this. Maybe that wasn't me. Let me show you this one first because it follows, and I'll go back. This is a study of using an eye tracker to look at foveation on chessboards to solve chess puzzles. You know, this kind of thing like take the king in 4 moves or knight and whatever it is. And what you're looking at here is the difference between novices and experts. In red, experts, yellow, novices. What experts do is they barely look at the board. They don't waste their time, right? And intelligence in chess is economy of effort. You do less looking ahead, not more. It's completely weird. It seems to be contrary to the way we've thought about intelligence. Right? Well, because that person is amazing because they can calculate all these things in their head. If you're smart, you don't have to. So I just want you to jump to that. Now, there's lots of work in this area of what's sometimes called extended mind or cognitive artifacts, and people like Hutchins and Donald Norman and David Chalmers and others, and Andy Clark. And this is the kind of famous paper that put the extended mind on the map. And in this paper, they said, it's true that the brain stops at the boundary of the cranium, but maybe the mind doesn't. Maybe the mind is something much more diffuse. Maybe the mind lives more out of you than in you. There's a kind of condition that if you don't have a brain, you won't have a mind, but it's necessary, but not sufficient. Okay, I just wanted to put that up. It's a very interesting paper. It's worth looking at. And I go through, but it doesn't matter. So what is learned in all these studies? If I were to summarize very quickly for you what we've learned over the last, 30 years of cognitive artifact stuff. One thing, right, is that harder tasks tend to recruit more neural tissue. That's a generally true statement. That shouldn't surprise anyone, really. But experts, I'll just say the statement, but experts solve problems more efficiently. So easier for experts, but still need more to solve a harder task. Yes?
So the statement you just made suggests that more tissue is helpful.
Yeah.
So, but this extensive scaling up, I think about facts that have happened in history that person, human, uses a gigantic portion.
Yeah, it's very interesting. Yeah.
And yet, their intelligence seems to be unaffected, maybe their person.
Yeah, the so-called Phineas Gage, you're thinking of Phineas Gage. Yeah.
Scaling, is it like short time scaling or, power level or something like that? It doesn't seem like more, it's more matter.
Yeah.
In maybe some time.
So yeah, you're right. But I want to clarify the point I just made because it relates, I think, to your question. So harder tasks typically are associated with a greater volume of activation. But as you get expert, that shrinks. So expertise, according to Erickson and others who work on it, is a recoding, a new representation which is more efficient and compact. So actually, so these two things go hand in hand. So it's almost like, if you're familiar with random function theory, if you're trying to fit data, the way you actually approximate a fit fast is you throw some huge, ugly polynomial at it. But then you prune it, right? But if you start with a low-dimensional representation, probably you won't hit it. And that's what's going on here. You start with this quite inefficient, large expanse of tissue, and then you recode. So it gets to a little bit to the question of why we appear to be robust. Because a lot of that tissue wasn't needed in the performing phase. It might have been required in the acquiring phase. Do you know? So could Phineas Gage, who famously lost part of his frontal cortex, learn? And that's he became horrible, we know that. But we don't know. So that's.
So is it kind of system to system on delegation? Expertise is basically delegating conscious effort that happens.
Yeah.
System.
Yeah. So actually, my brother's not here for this.
Yeah.
So that's his field. So in the case of skill, there's a lot of data that you cache the policy. So you don't have to store it in your frontal. And that actually, I'm not talking about it today, but you can see that very clearly in terms of the early representation of a task, like when you're learning to use the abacus, frontal cortex. When you become expert, visual. So it's like caching. So it's like, John calls that the intelligent reflex. It moves from system 2 to system 1. Yeah. Okay, keep going quickly. Oh, and there's lots of data on the abacus, the same story, harder, more tissue, experts, less effort, over and over and over again. This is now, I think, what an economist would sort of call a sort of a kind of an empirical law. So now to investigate this a little bit more rigorously, we've been looking at some model systems, and the three that we've been studying are the Rubik's Cube, the Soma Cube, and the Pocket Cube. The thing about this is, people love these things. It's like, if you ask people to solve math problems, it's like, oh, yikes. And how boring. But you take a child and they'll spend their whole day working on this kind of stuff. And I was saying yesterday, I wanted to make a New Yorker cartoon. And the New Yorker cartoon has a kid with a Rubik's Cube, and mother comes into the room, or father comes into the room and says, stop solving problems in advanced group theory and do your fractions. And it's actually, I'm quite serious. Why? This is a problem in group theory. Identical, isomorphic too. And yet we fucking love it. And so, and just some facts, this has sold 500 million units. 40% of all sold puzzles are Rubik's Cubes. It's really, really hard. And so why am I interested in this? I think they do lots of interesting things. And I'm going to try and explain to you what they do. I think with the Soma Cube, I'll get to at the end, I think it gives us new ways of thinking about cognition, what thought is, what mind is, what the extended mind is. That goes quite beyond, actually, Clark and Chalmers and others. The Pocket Cube's nice because it's quite relatively low-dimensional. It's still massive. But we can enumerate the full search space. And we can create virtual agents that solve it to see what the algorithms do. Can't do that with the Rubik's Cube. It's just too big. But with the Rubik's Cube, we can actually study competitive Rubik's Cubers, and we work with some to see how they're solving the cube. So it's kind of a nice spectrum. Each puzzle has its own unique contribution to make. And so here's my collaborators on this section. Gulce, who's online somewhere, I believe, who's between SFI and Boulder. Josh, also between SFI and Boulder. And Ben, he's got the best affiliation. His affiliation is not a university, but the World Cube Association. Here's my advice for you. If you're working in an empirical area, work with an expert. Chances are what you think is going on is nonsense. And it's a kind of humility that is actually also quite joyous because you learn so much from working with experts. So let's just talk about the Rubik's Cube quickly. It was invented in 1974. It has 43 quintillion permutations, states, solutions. Interestingly, the diameter of this thing, the shortest path from any bad random configuration, meaning the most jumbled, to the full solution is given by the diameter of the graph, which is the God number, which is 20. That's now known. It's only known for the 3 by 3 by 3, not for the 4, 5, 6, or 7. but we have a scaling law that Eric Domain here at MIT worked out. These things, as you all know, how many people here solved the Rubik's Cube? Enough of you, right? So you know how you do it. You do it with algorithms that you find online. And how you solve it. It has a very interesting history here. It's also solved blindfolded. And here's the interesting distinction. If you're a really, really good solver of the Rubik's Cube, you learn thousands of algorithms. Not 10, not 20, not thousands. And for special cases, that's what you're sort of doing. And blindfolded, you have to also memorize the entire cube in your head for the entire duration of the solve. And so you typically solve it with fewer algorithms. It's a kind of interesting trade-off. And these are solved using methods called memory palaces, which is another project I'm happy to talk about. But anyway, so there's a very interesting trade-off here. And so they tend to be slower, so you remember the full thing. So that's the cube. This, by the way, is a very crappy graph. I can't believe I'm showing a crappy graph at the Network Science Institute. Kind of like get the fuck out, you idiot. This is like a total heresy. Like, what the hell is that? It's not a network. Anyway, I just want to say these are networks, actually. But they're like non-visualizable. I mean, it's huge. And what they're comparable to, and so I was born in Hawaii. You wouldn't know it from my accent because I was raised in Portugal and England. But I'm a big fan of Polynesian navigators. And, you know, Polynesian navigators, right, they're navigating like 15 million square miles of open ocean. And they don't get to see any land masses when they're doing it. So European navigators, you know how they navigate? They navigate along the shoreline. And occasionally get lost and so cool, and then discover things. Okay, but Polynesian navigators don't get lost. I mean, it's a fascinating story. And so they actually have a very sophisticated, the point being, right, that you only have local cues. That's the point. If I could see everywhere in the world, there's no navigation problem. And they have this thing called the star compass, which is actually remarkably like the Rubik's Cube. And so you're using local configurations, in this case, stars, where the sun sets on the equator, current flow is amazing. So that local cue tells you something about the global position you're in the Pacific Ocean. So actually something I'm trying to do now is show actually how insights from the Rubik's Cube actually give us insights into navigation. Okay. So this is what happens, right? You have this graph, it looks nothing like that. It's got 43 quintillion vertices. And, you know, when you're solving it, you're moving through this. But what an algorithm does is it induces what's sometimes called a hop set, which is a shorter graph. It kind of rewires it, right? Such that, I didn't do that here, such that you can follow much shorter paths. So an algorithm is basically a specification from any given configuration, how you should move most efficiently to the target. That's what they do. Sometimes called macros, shortcuts, as a whole. And so here's the point, right? It's a little bit like the small world insight that there's this peculiar, despite its enormity, there's a small number hiding in it, which is its diameter. It's not the only number hiding in it. And so given that the cube is just about half-face turns or full-face turns on up, down, side, left, right faces, the solve time then, if you have God's number, is just given by motor skill. And the 3-second barrier just got defeated, which is mind-numbing. If you've ever seen it, say, here you go. Okay. And so, okay, so it's interesting. So that was a kind of bound, the God number, on the solve time at the limit of skill, right? And, you know, there are online sites where all of this data is available, and that's what we've been looking at. Tons of statistics, who's involved in competition, how many years. Another paper on their lifespan, the competitive lifespan of Rubik's Cube is very interesting. Blindfolders have short competitive lifespans, sighted have long competitive lifespans. It means if you record your first record breaking to your last, how many years does that span?
So just like youngness of the who has a blindfolded?
No. I think it's something intrinsic about the difficulty of the task and the tiny competitive advantages you have. But that's a whole. So how does this work? By the way, this is the social network of competitive Rubik's cubers. Each of these numbers is a cube. There is an edge between cubes when someone breaks a record on both of those cubes. Right? So you can see it's kind of an interesting and surprising structure. And this is just the color coded by the community structure of the graph. And it's kind of interesting and shocking, right? You'd think, so this is the easiest cube, it's the one everyone knows. But actually, and this is the sighted community of solvers. This is the blindfolded community of solvers. And it's interesting that it's the 4 that is the connective tissue between the two communities, not the 3B, but the 4B. You'd think that the natural extension of solving sighted would be to go 3B, but it's not true. And there are reasons why that might be true, which I'm not going to talk about, but just so you know. So it's kind of a cool world. The basic idea of everything I'm going to tell you now is encapsulated in these kind of equations. There is some world omega that at some time encodes in a community decentralized algorithms that we all get access to online. It also encodes tricks about skills, how you get faster. It also encodes ideas about how to make a cube out of magnets that can be solved more quickly, right? And there's a kind of final term there, which is the kind of representational fidelity of the underlying task that the artifact gives you. So what is an artifact? An artifact maps, right, a world onto a sensory object, a tactile object, a perceivable object. So the Rubik's Cube is the projection of the 43 quintillion dimensional Cayley graph onto a physical object. A map is a mapping, right, from the physical world that we live in onto 2 dimensions of space. So artifacts are essentially encodings of reality. And you can actually study how good that mapping is. And we talked about it yesterday. I'm very interested in the difference in a map and GPS, for example. What makes a map an interesting projection in a way that a GPS is not? They both do the job, but one of them fosters total dependence, and the other one fosters independence. An LLM, sorry, Brandon, might be a GPS, I don't know. Or it might be a map, and then that would be an interesting conversation. And so what happens? So this is the performance from that database of cubers through time. The blue is the number of moves it took to solve the cube, and the yellow is the time. These are exponential curves, right, which is interesting because most people who study skill are interested in power laws, but these are exponentials. And you can see that they're exponentially improving and saturating, like I said to you, because you can't really do better than God number unless you're lucky someone gives you like a solved cube. Did it! 0, I'm the champion, you know. It happens, by the way, in competition. Not that bad, but, and interestingly, on the right is what the computer scientists said the God number was in time. So these were the best solves in a given year, and on the right was the computationally calculated diameter of Rubik's Cube. And it's really interesting how children solving a puzzle are doing basically as well as overpaid academics in computer science departments. Well, that's true. Actually, to be fair, the computer scientists actually win this one. They get to good numbers first, and so, but only for the 3 cube, 7 or the 4, they're not there. So that's kind of fun that this was happening, that if you were a mathematician, you were looking at the competitions because it was telling you something that you didn't know. kind of cool. It's not clear how many other fields have that character. So what's going on here, just so you know, is that this is a collective intelligence curve. Because, for example, 2004, both in time and number, is actually the average of several record-breaking attempts. So this is a kind of averaging over the performance in any given year. So these, what we call performance curves or progress curves, are actually collective progress curves. That's not an individual performance. That's the population.
Just a side note, like there are other examples of this that are part of the approach in groups, like in online competitive games, like AlphaStar was working in StarCraft, but there's an example of like 20 years, a whole group of people playing this. The bar is much higher than it used to be.
Right, it's interesting. So one of my collaborators, Sung Woo, has been working on Nintendo speedruns. And so all these worlds, I got very interested in a game called Super Hexagon. I don't know who's played it. Oh, it's so hard. It's a great game. You last 4 seconds, you think, I am a superhero. It's so difficult. But there are, you're interested in these model systems that can be formalized. They have a mathematical treatment, and they have this kind of data set associated with them. And that's a kind of a sweet spot. And I think video games is something where there's lots of that. The problem is most video games are too complicated. Tetris I find very interesting. That's the one I kind of want to go after. Yeah.
In regards to like artifacts being maps to some world, when we're talking about intelligence or something being a efficient like movement in that space, I feel like there's a lot of cases where it's not the person who's using the artifact, but the artifact itself has intelligence.
Yeah.
Because
yeah.
and obviously it depends, but like if you have a Rubik's Cube and like each tile or something represents a very large combinatorial thing in the mapping, then isn't the artifact that's involved?
Yeah, it's very interesting. I don't have a good answer to that question, actually. I think that the way I think about it is scaffolds for intelligence, and the formalism tries to deal with that, actually, which is how do different puzzles vary in training you? And so there's a kind of intelligence in the design, right? That's a great design. They do limit moves, right? And so they induce the graph. But that's the level at which you could imagine a Rubik's Cube where I rigged it such that after one, because I had lots of springs in it, after one turn, it was fully solved. I wouldn't describe that as intelligent because it's just giving you the answer. But I think there's something very profound there about puzzle design, and it was something we talked about with John Kleinberg, right? You want to sort of design something such that I kind of elicit from you the maximum representational capacity.
Would it be fair to say that the spaces themselves are the knowledge, like whatever we're talking about in regards to space knowledge, whatever jumps you make to any other kind of spaces or apps would be the intelligence?
Well, it's interesting. So I think, let me get to this, because I think they're all part of the intelligence. Expertise, knowledge, sensory motor skill, and sort of artifact contribution actually all go into the equation. I consider skill a part of intelligence as well. I think this is very unfortunate in sport where people say, I actually consider great athletes very intelligent, right? And they're doing problem solving effortlessly. Yeah. The fact that we think, that skill is this kind of weird pejorative nonsense, which is just not foundational. And so actually you can look at all of the cubes. So this is all of the 3, 4, 5, 6, 7, where we have competitive data, and something falls out which is totally shocking, which is they're all the same curve. And in fact, okay, I'm just going to do this very quickly because I want to talk about other puzzles. But you can think of the cube as being like a gambler's ruin. You take the cube here and you're going to kind of move forward in space at a certain rate, which is the probability of forward motion. Now you can write this down in one dimension because the measure is invariant, because the branching ratio of the cube is fixed, right? You don't have more options at each step. You have the same number of options. So the volume of the measure is the same. So that's why you can write it as a one-dimensional random walk, a gambler's ruin problem. And the gambler's ruin is well known. You can solve this quite easily. And the gambler's ruin is given, the expected absorption time is given by this ratio, which is a ratio of the forward, this is the God number in one case, and over the forward drift term, which is based on algorithms. How fast I move through that graph depends on how many algorithms I store. And if you just rescale it by the God number, they will collapse. It's kind of a shock, by the way, because the larger cube is exponentially harder, but it's actually not harder. It sort of depends how you define difficult. We're talking about difficulty and complexity. For me, these are all equally difficult, right? Because of the universality of the exponential, even though it's absolutely more difficult because it requires more algorithms. But you know, this doesn't give you much of an insight. You say, well, yes, but why are people getting better? It's interesting that they do scale this way. And it turns out that you can calculate, for any one of these progress curves, you can infer a learning curve. All the learning curves have exactly the same rate of improvement. They only differ on their inflection points. So the way to think about this is, omega is the community of stored algorithms. You're sampling from that at the same rate, depending on whether it's a 3 or 4 or 5, 6 or 7 cube. But the number of algorithms you need to successfully solve the cube does vary, right? And that shifts the inflection point. And so these things predict precisely how much knowledge is required to solve the cube, essentially. And you can be clever about it, and this is blah, 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 all to say, you know, what this tells us right there is an underlying structural regularity. There is this thing we're calling macro transferability, which is that if you know how to solve the 3, chances are you can do the 4 and the 5. So there's some knowledge transferability. There's skill saturation because they all have the same exponent, the parameter, the coefficient of the exponent, same rate, same skill. And universality can derive from some basic assumptions. So we can now kind of wrap up the Rubik's Cube. Oh, before I do, blindfolded. The interesting thing about blindfolded is you don't have the artifact in your hand. So you have to memorize the artifact. And something really weird happens if you look at the competitive data on the blindfold. So this is no longer, okay, but they start off much slower than the sighted, but they improve much faster. This is learning memory techniques. Irrespective of the cube, whether it's a 3, 4, or 5, you don't do 7 blindfolded. They then converge on the sighted at 8 years. Exactly. I have no idea why that's true. So the community has found the way to do this effectively, and now all the cubes are of equivalent difficulty, and you're behaving like a sighted. Okay, so basically over here, you're in the skill realization phase, and here you hit the knowledge ceiling phase. And by the way, this is for you, Tina. This is me asking Claude, please make me a figure in LaTeX that summarizes the insights, and it's shit. Yeah. And I want to point out this, see that little thing, and I put this deliberate, this is for you. I could not get it to move that. You know that little gray thing in the middle? Move it. Anyway.
You have to think more algorithmically.
I think you have to go down a level. Yeah, I was not going down a level. Yeah.
It's different representational fidelity.
I think you're totally right. Yeah.
Because you don't have to, like you're not limited by a model still time.
No, because it gets to the original observation by Chase and Simon. Chunking is perceptual, not cognitive. And this is really interesting. So you know this sort of Rain Man type story. You see, you look at some set of objects, and there is some number, I think 7 plus or minus something. Is it 3? I don't know what it is. And where you can see it as a unity. You can see it as individuated. And that capability is perceptual. And so if you're given a cube sighted, you can see corner pieces like this, whereas in your head, you have to actually recall them. So there is a delay. It's very interesting, actually. It gets to this point that I think intelligence is perception, not inference. Intelligence is representation, not calculation. That's why all you Bayesians, give it up. It's not about Bayes' rule. Okay, yeah, Bayes takes as a given the representational problem. I would much rather re-represent the problem than run it on Bayes, right? And not do Bayes on a silly representation, which is what silly people do. Okay.
Shots fired.
Shots fired over the bow.
Since you questioned or
Oh, no, I don't need to do this cool stuff. Sorry, people, you just have to wait. It's your fault. You interrupted me. So you asked for it. So I just want to show you, this is, now we want to look, I want to look inside. And this is very cool. I might skip the soma, but I want to tell you about this one. Because the thing about the Rubik's Cube is it's so big, you can do phenomenology, you know, and I can make models which are kind of, I think are what's going on. But now with this thing, you can look in it. And I just want to show you a few statements of things that we've been finding with Gucci and Ben. There are beginner's algorithms, intermediate algorithms, and advanced algorithms. Well, how are they different? The number. This is the number of algorithms that an expert solver uses to solve the pocket cube, which is the 2x2 one. And notice something interesting here, by the way. The beginner's algorithms still have very long macros, so the number of moves in that particular algorithm. It's just they're much less dense in the space. And okay, so first, expertise here is knowing more. Okay. What does it do? What's the more is different? Here's the interesting thing. So look at the one on the right. Forget that one. That's just above God number. This is basically the number of moves, the distribution of number of moves to solve the cube under the different algorithms. So this is fully enumerated space. You can implement these rules algorithmically now. These aren't people, virtualized people. And you can see something really interesting here. Does anyone see what's weird that's going on? Bimodal, that's what I was, not flipping colors. Bimodal is what I was after. Bimodal. Experts are unimodal, beginners are bimodal. And what else might you say about that surprising, about the bimodal result? Yes, thank you. So very good. So let me say, beginner's luck. We've been trying to formalize the idea of beginner's luck. So what you see with beginners is actually sometimes they perform just as well as experts. And there's a kind of intuition we have for beginner's luck, which I think is wrong. It's like, oh, you just got the right deck of cards. Boring. This is a much more interesting one. It says that there are configurations in the initial conditions such that the algorithms that you have will take you to the solution as well as an expert. It's about the algorithms and the state space. Whereas, right, what the beginner's luck is one concept, but the new concept we've been introducing is beginner's stuck. And the beginner's stuck concept, which is, I think, more important than beginner's luck, which is that they also have these hot, crazy tails where they actually, the algorithms they have are not sufficient to take them to the solution. And in fact, you can kind of formalize it, think of it this way. There's some space, some sort of states, and what experts do is the algorithms move them through states in this graph, and they very rarely come out of book. Now, people who play chess know what in book and out of book means. So when you start a game of chess, you're in book, because you don't do anything original, just you play the move. Expertise, paradoxically, consists in staying in book, which is kind of like saying being an expert is not being creative. But it's true. I hate to tell you, if you actually sit down with a really good mathematician, what happens? You say, I don't know what it is. And they say, I know what that is. That's this. And then you solve something. And you say, oh, now what's that? Oh, I know what that is. That's this. You know. So being expert means keeping everything in book. And that's what these people are doing. And being beginners stuck is being out of book. Right? So you move to a state, I don't know where to go. And And the way you do this is use an AUF. So on the 2x2 cube, you just move the top layer, upper layer, until it falls into a configuration which is in book, and then you straight then back into book. And so these distributions are reflecting this kind of dynamic. And I just wanted to say, blah, blah, blah. I do believe that, generally speaking, this is what it means to be creative. These puzzles are giving us insights into problem solving generically. This is Mariam Mazzacani, fantastic, as you all know, Fields medalist, died very young. Mathematics is like a puzzle with infinite pieces, waiting to be put together in new and fascinating ways. She's using the metaphor of puzzles to understand what mathematics is. We can go further than that. Here's Roger Federer, and he says, negative energy is wasted energy. You want to be a master at overcoming hard moments. Get rid of the beginner's stuck tail. So, you know, I think for a lot of people, I remember talking to a fellow graduate student, Sebastian Bonhoeffer, many years ago. And he said, there are people who are success motivated as students, and there are people who are failure motivated as students. And he said, I'm failure motivated, him, not me. And I don't know what I am. But he said, I'm failure motivated. And I think he meant, I'm going to spend a lot of time getting rid of those tails. And I think that's kind of an interesting insight. So I'm not going to talk about this bit, even though it's the best bit. And, but it's just fun. The story, the history here is that Heisenberg was giving a lecture in Copenhagen in quantum mechanics in 1933. And in the audience was a young physicist, his name is Pete Hein. And he was bored out of his mind, like some of you are now. And he invented, while he was in that lecture, one of the most popular puzzles in the world. And this puzzle is not like the Rubik in the pocket, it's a skill puzzle. It's not a knowledge puzzle. And it's called the Soma cube. And it's the complement to everything the Rubik in the pocket is. I'm going to show you slides because I'm so excited about it. It looks like this, it's got 7 pieces. You have to assemble them into a cube. You can give this to a 3-year-old or 2-year-old, they can solve it. They don't need to know, they know knowledge. So what's the difference here? And here's the cool thing, and it's almost the only slide that matters, which is this one. This is actually not true, it's 8,000. In the same way that the Rubik's cube is the Rubik's group, the 43 quintillion vertex Cayley graph, whose edges are the generators of the group, the Soma cube is an 8,000 clause in normal disjunctive form Boolean satisfiability problem. So this is the piece number, and these are the 3-dimensional coordinates in 3 space. To solve the cube in your head, you have to set all these up such that it equates to true. There is no human in the world, I hate to tell you, that can do this. It's isomorphic to the cube. Why is that hard? But a child can solve the Soma. And the reason is, instead of algorithms inducing subgraphs, the Soma induces subgraphs physically. Terms, some of these clauses fall out by virtue of the exclusion principle. So physics, basically physics does for the Soma cube what algorithms do for the Rubik cube. So this is, we call this the principle of materiality, which is how do materials drop clauses out or refactor or shorten what would otherwise be very large search trees. So, okay, I'm skip all that. And do I have a nice thing? For those interested, just at the end, I'll put these up. For those interested in more popular accounts of this kind of thinking, I put these up because these are more readable papers. You can find them all on that website. So if anyone's interested, non-technical things. Thank you very much. Welcome. Yeah.
So if you do yes, please.
So I was more interested in terms of the representational fidelity.
Yeah.
Like,
yes.
You know, is it static? Is it dynamic? Is it a black box? Is it a white box? Like, there's many different dimensions.
So that's a whole thing in itself.
Yeah.
So there is an equation, yeah, and I know this is not what you asked for, but I just want to show you some, where it is anymore anyway. So,
Because when you were talking about the artifacts, you were talking about the representational fidelity, and if you go to the complementary versus competitive artifact, it has to do with that representational fidelity.
Yes. So basically, each one of these terms is a whole thing unto itself. And if we look at this term, what is that term? It's a very important point. And so this term actually technically is the ratio of the mutual information between your perceived current state and the actual state of the world. So it's like how much of it you see. And it can be encoded in two ways. It can be encoded by a direct mapping between world and artifact, or it can be encoded in your internal representation of the artifact. Okay, so I let you memorize the key. So that's the first thing. The second point is, what is it about the artifact that allows you to internally encode it? And that's its local versus global character. So if you're learning an artifact, the thing about the cube is you can form a full global representation of the cube. And if I give you a GPS, you can't. It's totally local. If you were going to try and reconstruct a map of Boston from driving with your GPS, it would be kind of crazy, right? It's like that, go top, forward, go left, go forward. And so actually, so where that notion of what I've been calling artifact transparency comes into play is in whether it's a local or global representation of the world. And
it's local, it's transparent?
It's more transparent, correct. So yeah, if you think about something like, people here use the abacus. So the abacus is very interesting, this is called Anzan, which is the blindfolded, the mental abacus, the abacus you use in your head. And think about the abacus, you do the whole thing. And so when you're solving an abacus in your head, right, if only had like one rung, it would be useless. That would be like a GPS. And the question that, actually, questions for discussion that I put at the very end, actually, for sort of LLMs, is my view is that if I think about extensive embodiment, what I call exbodiment, which is to the extent that intelligence is extensive, to the extent that we can store more states in the world, everything I've been telling you about, to the extent that these objects can be partially inferential and all the rest, they do these things. They extend working memory, they extend inference, they reduce search spaces. Hopefully you now buy that. But they also do these other things, right? They promote efficient encoding, like maps or whatever. They promote collective intelligence because we work on the Rubik's Cube together, right? And we share through Omega, through the collective search engine, right? And I would actually argue that AI strikes all those off. That there is a fundamental qualitative difference between the Rubik's Cube and an LLM. Now, you could build, I think, a system of LLMs that try to reintroduce, actually, those elements. Not that it's something about the technology that makes it impossible. It's just that I think we need to be very thoughtful at this point in our history because we've gone from inferential artifacts that have these characteristics that have made us smarter to a new inferential representational artifact that has lost some of the critical elements. And I think we need to, as a community, put them back.
But there's this stochasticity there that you're not touching on, which is like the Rubik's Cube.
Yeah.
I know what it is and where this will happen.
Yeah.
The LLM is an artifact. I don't. It's dynamic, it's stochastic, right? And so I'm not sure if it reduces to local versus global.
In terms of I think it loses, Gina, I think it loses all of these. I think that, I do think it would be fair to say they do that. I mean, it does extend my memory, it does extend inference, that's why we're all sort of addicted to them, And so, and it does reduce search space. I mean, this is true. But I think when you say what it doesn't do, I think we're agreeing it doesn't do these things. And so why doesn't it promote efficient internal encoding? And I think it has something to do with its opacity. Whereas if you're solving a Rubik's Cube in front of me, I can see it. I can see the logic. If an LLM is solving a problem for me, I can't see the logic.
Right, but I think it goes to the, maybe we take it offline.
Yeah.
The thing of when it's learning versus after it's learned. So
Yeah. Yeah. I know that you had it. Yeah.
Fascinating about the idea you talked about as life as intensive and expensive.
Yeah.
I'm also thinking I'm like thinking about intelligence also as some kind of potential actually, like the potential to as the community, there's a potential to do information compression. So if we are like memorizing all the possible ways to combine a group, and then we just select the one that match the current space, and that's not intelligence in my mind. So I would think that would be like if you don't have the base rules and then you devise some way to do it efficiently, then randomly, then that would be intelligence. If you have the base rules, then intelligence will be to improve the potential to improve these rules.
Yeah.
So I'm thinking about whether there's another. So it's kind of like that memories and the expertise at the end would be some kind of like crystallization of the intelligence.
Yeah, I think we're in agreement. I think that what you're describing is the secondary encoding of the solutions, right? In other words, you can solve the cube like you do blindfolded quite inefficiently with 20 algorithms. You can solve the pocket cube, I believe, with one. And so intelligence does consist in efficient encoding of the representation of the algorithms, right? And so now this notion that it's a potential is interesting because I would say this is like a potential on the potential, right? So the first potential, I believe, in my simple case, right, there's the life potential, the selection gradient, RL type thing. But that doesn't tell you which algorithms you're going to use or how effective they are or where they come from. That just says, good job, right? This is the problem with all the enforcement schemes. That's why I don't like a Bayes rule. It doesn't tell you anything about the actual how you find the encoding. So we discussed yesterday, in the likelihood term is all of the model, right? The feed-forward model that has to be encoded somewhere in some computational sense. And that's missing from the scheme. So I think yes, there is this kind of surface, this gradient, but it is induced by a mechanism.
I'm going to intervene quick. So, Gar, I'll take yours. I'm going to do one online. Sorry, but we have to cut it off.
I'll be here, so you can ask it. Yeah.
Okay, so, you mentioned intelligence as a violation of expectation.
Yeah.
Given knowledge of context.
Yeah.
So, in terms of physics vocabulary, would it be fair to think of intelligence as a non-equilibrium process where it always responds in relaxation, and that will sort of be the ultimate?
I mean, I think that's true. I think it would miss some nuance that I'm interested in. It sounds a little Fristonian to me. And so I think that, but I think it's true. But I kind of would want to know what is the difference between me as a piano player and Oscar Peterson as a piano player. And that doesn't help me because what you just said is true for both of us. And I think that the part of the problem with theoretical frameworks that we all have to wrestle with as theorists is, does it account for the variation that we actually find interesting? And I think a lot of the coarse-grained statistics that we all mess around with actually don't. And so yes, and. Yeah.
I'm sorry, but we have time for one more from the chat. So this is a question from Francois Gu, who is asking, in the age of physical learning, so learning in physical networks such as networks of resistors or springs, some can do classification already. Is there a parallel to draw from the idea developed for the Soma cube where theory can reduce the problem space of physics and these physical networks converge into
yes. Andrea Liu at Penn has done beautiful work on this. And and there what they do is they implement neural networks as physical systems. And then you're actually trying to show what can be done by essentially the stationary action after some kind of